Hello ME400, this is another video. This time it's a closed feed water heater with efficiency 8.58. If you want to see the problem statement, pause the video here. And we're getting right into it to try and keep the video to a minimum length because these problems are pretty lengthy. So starting off, we are solving for the enthalpy of state 1 just using the two state points given. Our state points given were 16 megapascal and I think it was 460 degrees C or 560, my apologies. And this gives us a H1 value of 3465 and 6.51. 3.2, I guess, if you want to get fancy. And from there, we move on to solve for the quality of state 2 using the perfect turbine assumption of S1 equals S2S. And so from that assumption, we get a H2S, or we can get a quality value for state 2, I guess perfect state 2. It's basically the same as every other problem that goes through a turbine with efficiency. You have to do this. So at times during this video, I'm going to just kind of I'm going to write out the numbers instead of the equations. You should know these equations, but if you don't, you can always just look them up in your book or see a previous example. And so after a little bit of writing here, we get a quality value. This is just the tedious part of doing these questions. It's just solving for states. I understand. I took the class too, so you just got to do it though. And I think with the end of this, if you want to skip ahead, I think we end up getting a quality of 98.983, which is really high. And that will come into effect when we start solving for state. When we start solving for state, I think 2, the perfect state, or the non-perfect state 2. The actual. Because if you remember on the TS diagram, when you have the non-perfect state doesn't go straight down, it drops to the right. And so you'll find later in the problem that there is no quality for the perfect state. It's actually superheated still. But we'll get there once we get past this tedious writing. I think this is where I made the decision to just start writing equations rather than writing out numbers. So you just insert, if you need to pause the video, just insert the values at the pressures, so like HF at pressure 2, etc. And you end up getting the value 2743.849 or 85. And so from there, we have to solve for the actual value of H2, which is using the turbine equation. So we have our efficiency of the turbine is 0.85, and we set that equal to H1 minus H2 over H1 minus H2S. And once this slowpoke gets done writing, we'll see that the enthalpy value is 2852.0 or 0.1. And that's just showing that we are solving for H2 here. You just manipulate the equation until you can get it. And we have 2852.1. It's like I'm a psychic. But this right here has some implications in the next part of the problem. We have to find S2. And so with S2, that's going to, because we know that through the next turbine, S2 is equal to S3S, and so we have to find, or through the second stage of the turbine, the low pressure, we have to find S2 for that. Because if we can't find S2, we don't know where to base our numbers. So to find S2, we have to first find, we have to see where H2 lies. Like where does state 2 actual lie in the mixture region, superheated, subcooled, etc. And so with this relationship, that I'm getting ready to write, hopefully. This is how you would find it if it was in the vapor region. You would have to find the quality. But the thing is, for our problem, we'll find that this does not have a quality anymore because it is superheated. This was just for your information, just in case your question did end up with a quality. You'd use H to find H2 to find a quality, and then you would plug the quality into that equation. But for our problem, if you go to the tables, you will find that our H2 value is greater than the maximum H2 value at 10 bars, which is 1 megapascal, which is our pressure 2. So with that means we know this thing is superheated. And this right here is just showing that. We know that HF is smaller than HG. And we also know from our problem, looking up in the tables, our H2 is greater than the HG listed in the tables. Which means we know it is superheated. Or as my bad penmanship would say, superhet. And so, from knowing that, we have to look in the, we go to the tables and we have to interpolate or guess, depending on, like how you guys want to do it. But I interpolated my value. Right now, I think this is where I went back and I think I erased something because I thought I was solving for the wrong number. But that H2 value is right. I think I realized that in a second. Yeah. I ended up rewriting it. I thought the H2 value we solved for was H2S, but I got confused for a second. So basically, from here, we interpolate in the tables at 10 bar, and we find where our H value is in between two, and we just kind of guesstimate where our S2 value is. And I think I write something as S2 is equal to 6.74 306, something like that. But that's a 6. I'm doing this on my laptop, alright? Give me a break. And so, from there, we know that S2 is equal to S3S. And we do the same exact thing we just did, only with the second stage turbine at the lower pressure. So I'm going to, I think, skip ahead here, because if I didn't, this video would be like 30-something minutes, and let's face it, that's way too long. So I think 20 is still pushing it, but that's for you to decide. A lot of erasing going on today. And so I make sure I write that. I say it's the same process. And the same process meaning we just use the turbine efficiency, and we find our X3S, we find our H3S, and we use the turbine efficiency to solve for H3. But only this time we do not have to solve for S3 because it does not go through another stage of the turbine. And right here I just write out all the values. And so here we have X3S is 8054. H3S is equal to 2109. .34, I think. And so then we moved into, so once we found X3S, we went to H3S, and then we used the turbine equation to solve for H3 actual. And I wrote this one out because the numbers change and it could be confusing, so this is what it would look like going through the second stage. And so we end up with an H3 value that is 2220.75. Well, 7485 or something like that. But anyway, so those are the values that we should take away from this page, our H2 and our H3 value. And then we move into the, I think the most confusing part when we start getting close to the open feed water heater, or the closed feed. So we know that H4 is just equal to HF at pressure 4, just the saturated liquid value at pressure 4. Because the condenser took the heat away from the steam and put the quality all the way down to 0. And watch my struggle to make an H5S. So, and now since we have H4, we have to solve for H5, which is after the pump. And we know the perfect value of H5 is equal to the perfect pump equation, which is H4 plus V4, specific volume of 4, times pressure 5 minus pressure 4. But we do not have V4 because I did not get it, because I do not have the foresight. So I had to go back really fast and pick it up, which is VF at that same pressure, P4, which is, I end up scrunching this up, so pardon that, but it is 0.001084. I just end up putting 8 there. So 0.001084, or 8 if you want to just put that. You'll get a very similar answer. So the pump doesn't really have an amazing effect on the problem, but it's still significant. So we have H5S to be equal to 190.01. And so we then use the efficiency of the pump to find H5. And so this is very similar to the turbine, except that the numbers are in different places. We have the perfect case on top and the non-ideal case on the bottom. And we are solving for H5. And once you solve for H5, you end up getting, let's see, 192.851. And so those are the values we should be taking away from this part, our H4 and our H5. The next part is pretty easy. This is probably the easiest part of the whole question. You know that H7 is just equal to HF at the second pressure, because when it goes through the condenser, or the middle part, the open feed or the closed feed water heater, it's a heat exchanger with the fluid going towards the boiler, and so we want to heat that back up a little bit, and so it's losing heat, and our pressure, and it's at pressure 2, so it preferably will lose all of its heat and become a saturated liquid. Like, it'll lose enough of its heat that it stays saturated, but it goes all the way down to liquid instead of a vapor mixture. And so we have our HF to be 762.81 at pressure 2. And since we know that H7 then goes through a valve, the property of a valve is H7 is equal to H8. The enthalpy does not change going through a valve. And then we move into H6. H6, this is the hard part of most of the questions. It might not be hard, but it's a little, it's hard to know if it's not said, but we know that H6 is equal to the saturated liquid value at Tsat, which is the saturation temperature, of pressure 2. Because properties of heat exchangers, when you're exchanging heat, the temperature of the fluid going through the towards the boiler cannot get hotter than the saturation temperature of the water heating it, right? So if you have a 40 degree water that's giving heat to 20 degree water, the 20 degree water cannot become like 80 degrees now without some extra help being put in. And so it reaches, basically that water going towards the boiler reaches the saturated conditions of the at the temperature of saturated of the water heating it. Yeah, it's a little confusing, but it makes sense if you look at the TS diagram and if you just think about how heat exchangers work. And then we have to find Y. Y is important, so we know the direction or the division of mass going between the closed feed water heater and the rest of the cycle after the turbine, stage 2. And a closed feed water heater, this is the equation for finding Y. H6 minus H5 divided by H2 minus H7, which gives us a value of 0.2766. And so we move on to actually trying to solve the question. So first up is the work net. And so the work net is equal to the mass flow rate of the cycle times the quantity, assuming this is steady state, so our mass flow rate stays the same. It is H1 minus H2, the work of the first stage of the turbine, plus 1 minus Y times, once I get to it, H2 minus H3. That 1 minus Y denotes that we are accounting for the mass leaving the second stage of the turbine. And then subtracting the work of the pump, which is H5 minus H4. And this value ends up being 1.26, or no, 28. 1.28 times 10 to the 5th kilowatts. Yeah, my screen's not very sensitive, so it has problems with little small curves, so bear with me. And so then we move on to part B, which is asking for the heat into the cycle. The heat into the cycle is just what we had to put into the boiler to get it back to high pressure, high temperature steam to make work from the turbine. And so that's just what the boiler put in, which is H1 minus H6 times the mass flow rate, which in our case equals 3.24 times 10 to the 5th kilowatts. And the final part is the thermal efficiency of the cycle, which is just the work net over Qn. What we want over what we had to put in for it. And we just found both of these values, so that makes things pretty easy. You just insert what we just found in its proper place. Work net being 1.28 times 10 to the 5th, and Qn being 3.24 times 10 to the 5th. Divide the two, and you end up getting a thermal efficiency of 0.388, probably could be 0.39, which I think is what the answer key had, but I like to write it out to a few digits anyway. And so your thermal efficiency, as I said, 0.388. 9. Never ending. Alright, and that is the last part of the question. Thank you for watching the video. I hope you learned something, and hopefully this helps you on the exam. And if you have any further questions about the video or some of the answers, just send them my way.